Okay, so since it's non-homogeneous, we now have a function g as a function of x, and this is not 0, right? And where p as a function of x cannot be 0, right? So you can still have q, well, p as a function of x and g as a function of x cannot be equal to 0. But these two middle terms can still be 0, okay? So the homogeneous equation, is known as the aka complementary equation, and the solution, so the homogeneous solution, is called the complementary solution. So this is what we did last discussion. Okay, so this is known as the complementary solution, or YC. So this is Y sub C. Or you can also call it I think another text that I've looked at calls it the homogeneous solution, so Y sub H. But in this book, they refer to it as Y sub C. And actually, this is a function of X. So I'll write that in there. Okay, so this is a function of X. And this could also be written as Y sub H as a function of X, okay, for homogeneous. So if we find the particular solution, Y sub P, and we'll say equation 1, we can combine Y sub P and Y sub C for the general solution. Okay, so this is a general solution to the non-homogeneous second order linear differential equation. So this is y as a function of x equals yp, which is a function of x, plus y sub c, which is a function of x. And this, so I've mentioned particular solution in the past, and this is not to be confused with a particular solution to an initial value problem or boundary value problem. I know it's a little confusing, so actually moving forward, I will no longer refer to these as particular solutions. I'll just say it's a solution to an initial value or boundary value problem, okay? So the particular solution is still a general solution, okay? It does not require an initial value or any boundary values, and it'll have constants in it, right? So it could have many solutions, an infinite amount of solutions. So one way of there's many methods in solving these second order non-homogeneous solutions, but I believe we're only going to be going over the method of undetermined coefficients. So remember, when we were dealing with first order, we had a couple different techniques. We had the linear first order as well as a separable, and there were two different techniques of solving different classes of differential equations. And there's also different techniques for second order non-homogeneous, but right now we're only going to deal with the method of undetermined coefficients. So based on our g function, g is a function of x, we can guess a reasonable, we're not just pulling this out of thin air, a reasonable particular solution. Okay. So, reasonable particular solution, y sub p, and basically we'll solve for the coefficients. Okay. So we'll look at a few different cases here. Let's start with A. So if our function g as a function of x is a polynomial, okay, we would guess that our yp would be ax squared. So we start with our highest degree polynomial with a coefficient in front, so bx plus c, all the way down to a constant. So we're reducing our exponents until we just get to a constant, and then we have a coefficient in front of each of these terms, right? So let's say you had, instead of just x squared, you had 4x cubed plus x. Well, in this case, your particular solution, your trial particular solution should be, it would start with the highest exponent, so x cubed, so a x cubed plus bx squared plus cx plus d, right? Pretty straightforward. We had this case here, g as a function of x. Let's say that equal e to the 3x. Well, this one, we'll just say is coefficient times the exponent itself. Okay. So remember back a couple weeks ago when we were proving that a solution is actually a solution to our differential equation. We basically took what our given solution was, and then we had to differentiate it and then plug it into our differential equation, and then we check to see that our left side equal the right side. Well, if you kind of look at the solution intuitively, it makes sense because the exponential term, when you differentiate it, and this is going to be twice because we have a second order, you're going to get itself, right? So you can see that this will the same function will manifest itself on the left-hand side when we guess for a solution, right? So when we're talking about polynomials, that's why we want to include all these terms. We want to decrease the exponents down from the highest power, because when we start taking derivatives, it's going to reduce our exponents, right? So if we were to prove this and we take two derivatives, if we started with x cubed, we know we're going to have terms x squared and x to the 1 power and potentially some constant terms. So in order to cover every single possible combination of terms in our solution, that's why we start with the highest power and reduce it until we have just our constant term here. So that's kind of the idea on how we're guessing these trial particular solutions. So let's look at part C. I guess this will be B, this is C, this is D. So D, we have g as a function of x equals sine x. So since sine and cosines, when you take derivatives, they alternate between sine and cosine. Our particular solution should include both. So it should include, even though this is sine, our g of x, or g as a function of x is in terms of sine, we want to include both a sine term and a cosine term. And again, this is because when we take derivatives, we're alternating back and forth. Whereas e to the 3x, it remains e to the 3x. So we don't need to enforce another term, any other types of terms in there. Okay, so we have a couple more cases. If we have the product, we can also have the product of any two of the forms from A, B, C, A through D. So we can have the product of A through D. So if we had a polynomial times, let's say, a cosine function, this is the product. Well, we're just going to, our trial particular solution is going to be the product of two guesses. So if we had just this x term, we would have had ax plus b, right? We're starting with the highest power and reducing down to just a constant. And we're going to multiply that by the trial particular solution for cosine of 3x, which would be in terms of sine and cosine, right? So what I'm going to do is say sine of 3x plus cx plus d, this in parentheses, cosine of 3x, okay? So when we have the product of two, product, we have the product here too, right? Product of two guesses, which is also shown here, right? So let's look at the last case. G is a function of x times e to the x plus cosine 2x. So now we have a product, but we also have two terms here, right? That's being added together. So this is going to follow. So we're going to look at this first term first, which is the product. So we have ax plus b times e to the x. So that would have been our trial for e to the x, right? And this is our trial for x. And we multiply those. And then now we look at this second term separately. And we'll have c cosine 2x plus, we also need a sine term because cosine and sine terms are cyclical when we differentiate them. So we want to make sure we cover both sine and cosine terms. And all we did was have a linear combination of these two, the solutions for these two terms. So we have one term here and another term here. This corresponds with this guy here. And this guy corresponds with this guy here, right? So this is coming from what's called the principle of superposition. So it's essentially saying if yp1 is a solution to, so I'm going to simplify our first differential equation up here. So instead of putting px and I'm just going to simplify it to these coefficient terms. A y double prime plus by prime plus cy equals, I'll call this g1x. So this, in this case, this would be g1x. And yp2 is a solution to a y double prime plus by prime plus cy of g2 as a function of x. So this would be my g2. Then yp1 plus yp2 is a solution to y double prime plus by prime plus cy equals g1 plus g2, okay? So now this matches our case F, right, that we have here, okay? Any questions on any of these cases?
So
now, yeah.
For like concrete templates for future problems, or?
Yeah, you can use these as templates basically. Yep.
Okay.
So there will be a special case which I'll address at the end, but for all of these, yes, you can use these as templates. Okay, so let's basically go through all of these examples with the exception of a couple of these. I'm going to skip B and I'm going to skip E. I'm going to skip B because A is essentially the same problem as B, and I'm going to skip E because it's the problem that I gave is a little tedious. So in the interest of time, I'm going to skip that one. But because this is a little bit longer of a section, the whole next discussion will be dedicated to examples and slightly harder examples. So we'll have plenty of opportunities to revisit all these topics. So let's look at case A. So our differential equation. So again, we're ending up with our polynomial there for our g as a function of x. And we're given our differential equation. So for all of these, and this will make a little bit more sense towards the end of the discussion, you want to start with finding the complementary solution or the homogeneous solution. Because recall that our general solution is our complementary plus our particular. We always want to start with get in the habit of finding the complementary solution first. Otherwise, you might end up doing a little bit extra work at the end. And I'll explain why at the end of the discussion. So in order to find our complementary, we need to find our auxiliary equation. We did that last discussion, and that's essentially matching the double primes with r squared, the prime terms with r, and all the y terms are just constants, and then the right-hand side is going to equal 0. Okay, so we're going to find our homogeneous solution first. So we're essentially finding our roots. So this can be broken down like this. So our R1 will equal -2, R2 is equal to 1. So this was case 1, if you remember back. Case 1 here, right? Real and distinct, you have two different roots. That's the form of the general or the complementary solution that we're going to have. So YC is going to be C1 e to the -2x plus C2 e to the x, right? So these are the coefficients here, just as a reminder. Now we're going to guess a reasonable particular solution, as we've outlined earlier. So since we have a polynomial, x squared, that's our highest power, a reasonable guess would be starting with the highest power. We go down to the constant, so that would be our guess for our trial particular solution. And now, in order to solve for these coefficients, we're going to have to plug in this guy and the derivatives into our differential equation up here. Okay, so that means we need to find the derivatives of these. So this would be 2ax plus b. Y double prime is going to be 2a. Okay, so now we plug 1, 2, and 3. So now we plug these into our differential equation. Right, so our differential equation was y double prime, so 2a plus y prime plus 2ax plus b minus 2 times y. So minus 2 times ax squared plus bx plus c. And that equals to g of x, g as a function of x, which is x squared. So remember, polynomials are equal when the coefficients are equal, right? And we did this when we were doing our partial fraction decomposition. When we were solving for the coefficients, we did a similar thing, right? We grouped terms that were alike and then made sure that their coefficients equaled out left hand and right hand side. So we're going to do the same thing here. So I'm going to look at all of my x squared terms. So that's going to be basically just this guy here with the multiplied by -2. So -2a will equal 1. 1 because the only x squared term I have on the right hand side is that x squared, and that has a coefficient of 1. So we can solve for a directly. This is -1/2. So now I can solve for, let's see, x terms. So on the left-hand side, we have 2a. We have -2b. So 2a minus 2b. And on the right-hand side, we don't have anything, so it equals 0. Right? So we already know a. -1/2 minus 2b equals 0. So -2b equals 1. And b equals, it also equals -1/2. Right. Okay, so lastly, we can use, we can sum up all of the constants. So we have 2a, we have b, and we have this c times -2. So 2a plus b minus 2c, and that also equals 0. There's nothing on the right-hand side as far as constants. And of course, we can plug a and b right into this. So 2 times -1/2 minus 1/2 minus 2c equals 0. So this will become -1 minus 1/2 is -3/2. So this is -3/2. So on the right-hand side, this will be +3/2. So c will equal -3/4, right? So now we can plug a, b, and c into our particular solution, our trial particular solution. So this is -1/2 x squared minus 1/2 x minus 3/4 or minus c. So there's our particular solution. And now our general solution is going to be our complementary plus our particular, right? So we sum those up. So our complementary we found here, right? So equals c1 equal -2x plus c2 e to the x plus our particular, which is -1/2 x squared minus 1/2 x minus 3/4. So here's our general solution. General solution. So just as a side note, this is a solution by itself, and this is a solution by itself, okay? So they will both satisfy equilibrium if you plug those in, but this is the most general case, right? Obviously, this is it's covering a broader spectrum of solutions that you can have, right? And we've discussed that before when we said a linear combination of two solutions is also a solution. Okay, so now let's look at part. Like I said, I'm going to skip B, and I'm going to go to C, which the right-hand side was the exponential term. So our G as a function of X is e to the 3x. Okay, so again, we're going to start with finding our auxiliary equation to find our homogeneous solution. So r² + 4 = 0. r squared equals -4. Therefore, r is equal to plus or minus square root of -4. And of course, this is equal to plus or minus 2i, right? And remember, alpha plus beta I, that's the general form of the polar, or the Cartesian form of this complex number. And our solution will be e to the alpha x c1 cosine beta x plus c2 sine of beta x. So our y complementary will be c1. So there, our alpha is 0 in this case. So e to the alpha x will just be 1. So we'll just have the terms on the inside. C1 cosine of beta is 2. So 2x plus C2 sine of 2x. Right, so there's our complementary. Now we'll guess our YP, which for e to the 3x, we said we're just going to tack a coefficient in front of it. Nothing else needs to be done. And in order to solve for this a, we need to plug yp and its derivatives into our differential equation, which means that we'll need yp prime. So it's 3a e to the 3x, yp double prime would be 9a e to the 3x. And we plug these into the differential equation, into diff eq. So we'll have 9a e to the 3x plus 4 times y, which is a e to the 3x. And this equals e to the 3x. We can sum these two up, so we'll have 13a e to the 3x equals e to the 3x. And of course, if we solve for this a, the coefficient in front of this is 1. So 13a has to equal 1. Therefore, a equals 1 over 15. Right, pretty simple. And now our particular will be 1/13 e to the 3x. Right? So our general solution will be complementary plus the particular. So complementary was c1 cosine of 2x plus c2 sine of 2x plus our particular, which is 1/13 e to the 3x. So there's our general solution to our second order differential equation. Let's see. Now we'll jump to case D. Which now we had a trigonometric for our g. So we had sine of x now. There's our g of x. So let's find our complementary solution. This would be r squared plus r minus 2 equals 0. We've already done this before. This is from the previous example, right? So my roots are -2 and 1. So y complementary is c1 e to the minus 2x plus c2 e to the x. And now we guess our particular. So this will be in the form, so we need both sine and cosine terms. Now we'll need to find first and second derivative so we can solve for our coefficients when we plug back into our differential equation. So second derivative will be negative a sine x minus cosine x. Right, so now let's plug into diff eq. right, so y double prime negative a sine x minus b cosine x plus y prime. So a cos x minus b sine x minus 2 times y, so 2a sine x minus 2b cos x, and this equals. So I want to gather all of the terms with sign in front of it, or sign behind it. So that's negative a, we have a minus b, and we have a minus 2a. This equals 1. So we used up this, and this, right? And this. So we're not going to be able to solve for both of these, obviously. So we need another equation. So there's one equation. So now let's try combining all the cosine terms. So we have a minus b plus a minus 2b, and there's nothing in terms of cosine, so it'll be 0. So we covered everything. So it looks like a is going to equal 3b, and then we can plug this in here. So minus 3 times 3b minus b equals 1. So minus 10b equals 1. B is negative 1/10, right? So we can figure out a from here. So a equals 3 times negative 1/10. So therefore, negative 3/10. So our particular, which is coming from here, is negative 3/10 sine x minus 1/10 cos x. Our y general is yc plus yp. So our yc was c1 e to the negative 2x plus c2 e to the x. And then our particular is 3 times sine x minus 1/10 cosine x. Okay? Okay, so I'm going to skip E because that problem is a little tedious, but it's the same procedure. Let's look at F, which now this one is, oops, not C. So now we have a product of terms and a summation of terms, right? So this is covering 2 different topics. So again, as before, we're going to check, or we're going to find our complementary. So R equals plus or minus 2. So our y complementary should be c1e to the 2x plus c2 e to the negative 2x. Now, in order to solve for this, I first only consider the first term. So I'm just going to consider this one here. I'll call this G1, okay? And then this one I'll consider as G2. Since this is the summation of 2 terms, and remember for case F, we said that we're going to use the principle of superposition, and that we can find the solutions yp1 and yp2 separately and sum them up to find the solution to when we have g1 of x and g2 of x being added up on the right hand side. So let's just look at g1 of x. So we'll look at the case y double prime minus 4y equals x e to the x. So this is for G1. so now our complementary is not going to change. We already found the complementary. It's not dependent on G1 or G2, so that just stays constant. So now we're going to guess the particular for case 1. So this will be a product of 2. So first, let's look at that one. That should be ax plus b. It's a polynomial, right? And then the second term will just be e to the x. And then the coefficients are taken care of in here, right? If you multiply that out, so the e to the x will have coefficients. So we don't need to put another coefficient in front of it. So yp1 prime. This is going to be a product rule. So first times the derivative of the second plus derivative of the first times the second. Okay. I can simplify this and say ax plus a plus b times, right? Not 2, double prime, yp1 double prime. So we'll take product rule again. So first, ax plus a plus b times derivative of the second plus derivative of the first, which is x times e to the x. And this is equal to ax plus, am I missing? It shouldn't be x, it should be a. Okay, plus 2a plus b times e to the x. So now we'll plug it into our differential equation. So y double prime ax plus 2a plus b, this is y double prime, minus 4 times y. So y is ax plus b e to the x, and this should equal x e to the x. Now I got to solve for my coefficients, so I'm going to gather all my x e to the x terms first. Doesn't matter what order you do it, but I'll do this one first. So my x e to the x, I have a here, right? If I distribute this e to the x in here, it'll be that. And I have this negative 4a here. So a minus 4a, that'll equal this 1. So minus 3a equals 1, therefore a equals minus 1/3. Now I'll gather all my e to the x terms. So we have, let's see, 2a, right? 2a plus b, and then minus 4b here, minus 4b, and this equals 0. We already have a, so 2 times negative 1/3 plus minus 3b equals 0. So b equals negative 2/9. Okay, so my y particular 1 is going to equal, so I plug a and b into here. I'll have negative 1/3 x minus 2/9 times e to the x. Okay, so that's my particular solution when my g of x is just equal this, x e to the x. And now let's look at g2 as a function of x. So y double prime minus 4y. Our g2 was this cosine 2x. So our particular for 2, not double prime, is going to be in the form, and I won't use a and b just in case. It might be confusing to use a and b again, so I'll use c and d, c and d. So now we'll have to have both cosine and sine terms, right? So we need to find the first and second derivative, so minus 2 minus 2c sine of 2x plus 2d cosine of 2x yp2 double prime is going to be minus 4c cosine of 2x minus 4d sine of 2x. And now let's plug those into our equation. So minus y double prime is minus 4c cos 2x minus 4d sine 2x minus 4 times y, which is 4 times c cos 2x minus 4d sine 2x. And as you can see, this can get pretty tedious. I think last year the homework problems there were homework problems that took front and back of one page. So yeah, these problems aren't necessarily difficult, but they can get pretty tedious. Let's see. So now we'll gather all the cosine 2x terms. We have a minus 4c here, minus 4c here, so minus 8c cosine 2x equals 1. Oops, I'll just drop the cosine here. So c is equal to negative 1/8. Now I can gather sine 2x terms, which we have minus 4d, and 0. So minus 8d equals 0, d equals 0. So my y particular for 2 is going to be minus 1/8 cosine 2x, and nothing for the sine term. Okay, so my y is going to, my general solution y is going to be yc plus yp1 plus yp2, right? Yc is way back here. Yep, c1 e to the 2x plus c2 e to the minus 2x. Yp1, can't remember what that was. That guy there, minus 1/3 x plus minus 1/3 x minus 2/9 e to the x, and plus or minus 1/8 cosine 2x, right? So this should be my general solution, right? Any questions on that one? That one was pretty long. And then now, so I said, we'll move on to the special case. There's a special case. And we'll do this through an example. So normally we would go through the same process. And this is the reason why we do the complementary solution first. So if we find the complementary solution, we see that this is r equals plus or minus I. Remember, alpha plus or minus beta I. So therefore, our complementary solution e to the 0x, so that's just 1 times, I don't even need that parentheses there, c1 cosine beta x, which is x, plus c2 sine of beta x, right? So this is my complementary. Well, if I was to guess my particular, disregarding the complementary, we would have chosen a sine x plus b cos x, which is essentially the same as my complementary solution, right? So we can't have that condition, okay? Actually, one of the key terms in the definition of the superposition was if you had 2 linearly independent solutions, the sum of those 2 solutions are also a solution. Well, these aren't linearly independent, right? These are exactly the same, or a factor of one another. So in order to avoid that, when your particular solution or terms in your particular solution coincide with terms in your complementary solution, you can avoid this by enforcing or multiplying the duplicate terms in your particular by x. So since we show a sine term and cosine term both in our complementary solution, we're going to multiply both of those terms with x. Okay, so now they're different, and now they are linearly independent. You may also, depending on the problem, you could multiply by x. So try that first, and if that doesn't work, you can even try multiplying by x squared. And generally, you won't have to do anything beyond that. So the book outlines trying x first, excuse me, and then if that doesn't work, then try x squared. So essentially, if this already had an x in it, obviously the sine term you can't just multiply by x. Well, in this case, it wouldn't even matter because they are different. But you wouldn't want to multiply by an x here because it would still be the same. So you can try multiplying by x squared. So you have the choice of doing either or. So now that we multiplied through by x, our particular solution is different than our complementary. And now we would go through with solving for the coefficients like we did before. So I only have 2 minutes, so I'm not going to get started on this. It looks like it may require another 10 minutes. So I'll actually pick up from this problem and solve it for the next discussion, as well as additional examples, a little bit more difficult examples from this topic. So, any questions for me? Okay, thank you guys very much. I'll see you guys on Wednesday.